Hi, Doc Revis here. In this video, I will show you how to carry out some calculations involving gases that are formed during reactions that involve gas law equations. We show you here some equations for the gas laws. We have Boyle's, Charles, Gay-Lussac's, Avogadro combined gas law. These 5 gas laws are comparative. In other words, you'll always have a starting condition and a final condition. You'll have one set of conditions versus a second set of conditions. So, Boyle's, Charles, Gay-Lussac's, Avogadro combined will always be comparative. That's one way to know you're using one of these laws. Then we have the ideal gas law. PV equals nRT. We also have an example here of a modification of the ideal gas law, which allows you to calculate mass or molar mass. Then we have density formulas here for relating them to ideal gas laws. And we also have a molar mass when we have density. We also note in this one standard conditions. Temperature is 0 C, but we always report temperature in Kelvin, K. Then standard pressure is 1 atmosphere or 760 millimeters of mercury. And an STP is important to note that 1 mole equals 22.4 liters. We have a conversion of 1 atmosphere to 760 millimeters of mercury or 760 torr. Note that when we use the ideal gas law equation, there are universal gas constants and we have to match those to the units. That is an important thing to remember, that matching the R universal gas constant to the rest of the units in the problem is very important. Let's work some problems. Let's examine a combustion analysis. And here's the problem. Calculate the volume of oxygen in liters required for the complete combustion of 7.64 liters of acetylene measured at the same temperature and pressure. That means that temperature and pressure are constant. So if we mark up this problem, we note that we have a V1 and we have a V2. We note that temperature and pressure are constant, therefore this reaction is responding to Avogadro's law, which states that V1 over N1 equals V2 over N2. We would then simply rearrange this equation to solve for V1. So V1 would equal V2 with N1 over N2. We could carry out this dimensional analysis straight away as shown on the far right, but note here, an important feature is that due to the unit analysis, it is proper to convert the moles to liters to match the rules of unit analysis. So, by Avogadro's law, the number of moles of gases are directly proportional to their volumes. Therefore, we can simply change the moles to liters. Therefore, we simply substitute in liters where we have moles, and those ratios are exactly the same. We get them from the balanced equation. So we take 7.64 liters of acetylene times 5 liters or 5 moles of oxygen per 2 liters or 2 moles of acetylene, and we obtain 19.1 liter. Put simply, when we carry out an Avogadro's law equation, we can simply use the ratios of the moles from the balanced equation for moles or liters. Let's do another problem. Sodium azide is used in some automobile airbags. The impact of collision triggers the decomposition to nitrogen gas, which inflates the bag. Calculate the volume of nitrogen generated at 80 degrees C and 283 millimeters of mercury by decomposition of 60 grams of sodium azide. A good habit is to simply mark up the equation with the variables. And if we mark up these equations, we note that we have temperature, which is directly changed to Kelvin, which we must always do. We notice we have pressure, and we note that we have it in millimeters of mercury, which we can directly change to atmospheres by dividing by 760. We note that we have volume in question, that is the unknown, and we have grams, but grams will get us to moles. Therefore, when we look at the variables, we see T, P, V, and N. And we note then that this can be solved by using the ideal gas law equation. We write the balanced equation, and it's very important that you use a balanced equation in carrying out all of these types of problems. So we take the ideal gas law equation and we rearrange it to solve for volume, where volume would be equal to moles times RT, with R being the universal gas constant, and in this case we use R in the units of atmospheres, divided by pressure. So we have all the variables here except moles. Therefore, let's first find the moles of nitrogen. We find the moles of nitrogen by carrying out a standard conversion or unit analysis or dimensional analysis, in which we start with a given of 60.0 grams of sodium azide, and it's converted to moles of sodium azide by using the molar mass of sodium azide, which is 65.02 grams per 1 mole. We then convert the moles of sodium azide to moles of nitrogen by using the conversion factor of 2 moles of sodium azide to 3 moles of nitrogen, which we get from the balanced equation. And this gives us 1.38 moles of nitrogen. We then take that 1.38 moles of nitrogen and we put it into our rearranged ideal gas law equation of 1.38 moles times the universal gas constant times the temperature, which is converted to Kelvin. We then divide that by the atmospheres, which we converted millimeters of mercury to atmospheres, and we obtain 36.9 liters of nitrogen produced from 60.0 grams of sodium azide. Let's work a problem where the number of moles in the reaction changed. Here's the problem. Aqueous lithium hydroxide solution is used to purify air in submarines because it absorbs carbon dioxide. By the way, it's also used in spacecrafts. The presence of carbon dioxide inside the cabin of a submarine having a volume of 2.4 times 10 to the 5 liters is 7.9 times 10 to the minus 3 atmospheres at 312 K. A solution of lithium hydroxide of negligible volume is introduced into the cabin. In other words, the amount of lithium hydroxide does not have an appreciable effect on the volume. Eventually, the pressure of carbon dioxide falls to 1.2 times 10 to the minus 4 atmosphere. How many grams of lithium carbonate are formed by this process? If I mark up my problem with the variables, I know that I have volume, I have pressure, I have pressure 1 and I have pressure 2, I have temperature, and I have grams, but grams will get me to moles. Therefore, since I see PVT and moles through grams, I know that I can use an ideal gas law equation for this problem. I write out then my balanced equation. I must have a balanced equation when I work any of these problems. So when I take a look at my ideal gas law equation, I can rearrange it to solve for moles, which will get me to grams. So here's my strategy. Step 1. Account for, that is, calculate the CO2 pressure drop, because we note that there was a change in pressure. There's a P1 and there's a P2. So anytime in an ideal gas law problem where you have two pressures, you must account for that pressure drop by taking the delta. And we'll show you how to do that. Step 2. Use the change in moles in a rearranged ideal gas law equation to calculate the moles of lithium carbonate from carbon dioxide, and we'll show you exactly what that means. In other words, when there's a change in moles, we must account for it. And in this particular problem, we have a change in moles and a change in pressure, and in the ideal gas law equation, we must account for them. Step 3 will be, or part 3, use the moles of lithium carbonate to carry out a standard calculation to find the grams from moles. So let's do this step by step. Let's keep in mind we're looking for moles, and we're going to take those moles to grams, and we're going to take it to grams of lithium carbonate, which has a molar mass of 73.89 gram per mole. We write out a balanced equation for this. We absolutely must have a balanced equation. We had already marked up our problem to identify the variables. And so the first thing we want to do is account for the pressure drop, the pressure change in CO2. And we do that by taking the final pressure of 7.9 times 10 to the minus 3 atmospheres minus the initial pressure. And this gives us a final pressure, or the pressure to use in our problem, of 7.8 times 10 to the minus 3 atmospheres. In other words, when carrying out a problem of this type that involves an ideal gas law and the ideal gas law equation, remember, if you have two pressures, take the difference in the two pressures. Now that we have our pressure, we can now calculate the moles. But note, we're really interested in the change in the moles. Therefore, we note that our delta P equals our change in pressure times the volume divided by RT. In other words, the way we account for a change in the number of moles is by accounting for the change in the pressures. Okay? So we've done that with the pressures, so we proceed to work the rest of the problem as if it's a simple mole problem. So we have our moles, but it's important to note that these are the moles of carbon dioxide. We're then going to take these moles of carbon dioxide and convert it to moles of lithium carbonate, which is our target for obtaining the number of grams produced. So we take the delta P of 78 times 10 to the minus 3 atmospheres times the 2.4 times 10 to the 5 liters divided by our universal gas constant times our K, and we obtain 73 moles of carbon dioxide. That is the gas produced. We would then take the 73 moles of carbon dioxide and convert it to moles of lithium carbonate using standard dimensional analysis approaches. In this case, we observe in the balanced equation that the molar ratio of carbon dioxide to lithium carbonate is 1:1. Therefore, if we obtain 73 moles of carbon dioxide, we know that that corresponds to, or is proportional to, 73 moles of lithium carbonate in a 1:1 balanced equation. So then, we effectively have 73 moles of lithium carbonate to work with. So to find the mass of lithium carbonate, we take the 73 moles of lithium carbonate and we carry out a standard conversion to grams of lithium carbonate by using 73.89 grams lithium carbonate per 1 mole of lithium carbonate, which is the molar mass, and we obtain 5.4 times 10 to the 3 grams of lithium carbonate. So, when carrying out a problem like this, remember to treat each step independently and be sure to pay attention to the molar ratios and the pressure drop. The pressure drop, or the change in the pressure drop, is what will allow us to calculate our delta N. But when we carry out the calculation of delta N, that is the change in moles, we simply carry it out as if it were simply a mole PV equal nRT problem. Let's carry out a calculation involving collecting moles of a gas over water. And here's the problem. Magnesium reacts with HCl to produce hydrogen gas at 26 degrees C and an atmospheric pressure of 752 millimeters of mercury, with a water displacement of 355 mils of water. In other words, when the gas was produced, it displaced 355 mils of water, which is the effective volume of the gas. How many moles of dry H2 gas was produced in the reaction where the vapor pressure of water at 26 degrees C was 25 millimeters of mercury? If we mark up our problem, we would note that we have volume, and it's in milliliters, but we're going to directly convert that to liters by moving the decimal over to the left 3 places, and we get 0.355 liters. We note that we have pressure. We note that we have temperature, which we will directly convert to K. And we note that we are looking for moles. So, since we've marked up our problem, we note we have V, P, T, and N. PV equals nRT. So we have our pressure volume equals the number of moles times the universal gas constant times T in K. For this problem, we're going to use the universal gas constant that has the units of millimeters of mercury to match our problem, which has millimeters of mercury. We've already converted our volume to liters, and we have our temperature in K. It's important to note that when you are carrying out a calculation involving collecting a gas over water, you must consider the vapor pressure of the water. And to do this, we note that the total vapor pressure equals the water plus the gas. Therefore, the gas of interest for us is hydrogen. Therefore, we take the total pressure of 752 millimeters of mercury, and we subtract the 25 millimeters of mercury of water, and we obtain a pressure of 727 millimeters of mercury to carry through in our calculations. Therefore, we take our N equals PV over RT, and that equals 727 millimeters of mercury, which is the corrective vapor pressure, where we consider P total equals P water plus the gas. We calculate out the hydrogen. So we have 727 millimeters of mercury times the volume, and we divide it by R, and the universal gas constant we use in this case has millimeters of mercury, and we also multiply that times the converted temperature from C to K of 299, and we obtain 0.0138 moles of hydrogen gas. So remember, when carrying out a calculation that involves collecting a gas or water, you must correct for the vapor pressure of water. Let's carry out another calculation. Oxygen was generated by the decomposition of potassium chlorate with 128 mils collected at 24 degrees C and an atmospheric pressure of 760 millimeters of mercury. calculate the mass in grams of oxygen gas, the vapor pressure of water at 24 degrees C is 22.4 millimeters of mercury. We mark up our problem and we note that we see pressure, volume, temperature, and moles. We actually see grams as what we're interested in, but when we see grams, we can think of moles. Therefore, this is a PV equals nRT. We write out a balanced equation. It is important that the equation be balanced. We note also that our T must be converted to K. And we also note that since it's collected over water, we must correct for the vapor pressure of water. Therefore, P oxygen equals P total minus P water. And therefore, we have 760 millimeters of mercury minus 22.4 millimeters of mercury. We calculate that through and we obtain 740 millimeters of mercury as our corrective pressure. Now, since we are looking for mass, we can use a modification of the PV equals nRT equation, which states that PV equals mass over molar mass times RT. We then rearrange that equation to show that mass equals pressure times volume times molar mass divided by the universal gas constant R times T in Kelvin. We put in each of these values, we check our units, and we obtain 0.164 grams of oxygen. An alternative way to carry out this calculation would be to calculate N and then convert it to grams. In other words, you would just add an extra step instead of doing it as one long unit analysis. In that case, you would calculate N by multiplying PV and dividing it by RT, and then you would take the grams and use a standard molar mass, gram per mole conversion, where grams equals moles times molar mass. So there you have it, a way of carrying out calculations involving collecting gases from reactions using gas law equations.